First of all, I have to excuse because I found that this is a very heterogeneous audience, so for some mix of stochastic characteristics is very, inconvenient for most of people. Instead, I try to explain something else, which is more figures. So, this is basically the topic was mathematics for application. However, this presentation is basically application itself of mathematics. So, how to apply mathematics in industry with other engineers. So, the other two persons, Kyung-Woo Kim and Ha-Yong Shin, they are the faculty members of Industry and Systems Engineering at KAIST. And he's very good at implementing some mathematical ideas. And he's another financial engineering major PhD. So, So basically, what I'm saying here is how to implement the financial mathematics for industry. So basically, it's about financial computation and to get around all the ideas as a platform, which is nowadays popular based on information technology. Basically why this kind of approach are necessary for nowadays in financial industry. Which is basically there are many financial companies and the industry environment is very competitive. So they need a faster algorithm, more accurate algorithm. So we need they need some support from academia. Of course, the math department in US, they don't need this kind of approach because the Wall Street firms like Goldman Sachs or Morgan Stanley, they hire many PhDs, more than enough. However, here in one of the biggest securities company like Samsung, the CEO of the Samsung Securities Company, they hired 5 math PhDs. Then after that, he is saying that, oh, we have 5 PhDs. Now we have enough PhDs. That's what they are saying. The other one is, now it's globalized, so we are competing with Hong Kong or even New York. So they need more help. And now Korean market has its own volume, meaningful volume. So we issue many derivatives. So that's another one. And what can KAIST do? So here the math is force. However, it's a physical level. Math is a deep knowledge. Okay? And the IT, it's fancy, but it's most shallow. So it's the order actually shows some level of depth. Furthermore, now it's not pure academia. It's industry-oriented application. That means engineering approach requires. And what many engineers did in manufacturing sectors, they applied computer-aided something, or some automation, or some optimization. So all these can be even applicable to financial industry. Why not CAD for financial products? Why not optimization for financial products? And so on. And the other one, even, nowadays, newspaper reports many accidents, the operational risk related accidents, right? They type in different numbers. The price and number of shares, they reverse, and that causes a lot of loss in their transaction. Yes. So it's some insight into the future, what will happen in near future from the past history. So I got the analogy from the old automotive industry. So just imagine beginning of the 19th century, or no, 20th century, when the automotives are invented and it is started to be produced. So usually it's the intuition of the talented technician that was the number one nowadays. And it's a handwork, right? And management, there is no such kind of concept because there are very few numbers to be produced. And in some sense, there was the knowledge system was physics and chemistry, and based on invention of automotive, mechanical engineering, had to be established by such kind of invention. How about the current derivative market in the sense of finance? Intuition of talented financial engineer like Nobel Prize winner Black-Scholes Merton. So they are very talented mathematicians or physicists. So they invented financial products. And they write down the code by themselves. So it's like handwork in the beginning of the automotive industry. And management, so many different codes in financial companies, so there is actually, it's a mix of codes. And actually there is something like the pure stochastics, like probability and statistics and finance. And by this kind of introduction of new products, the financial math or financial engineering, the area is getting established. How about current automotive industry? Now there is no intuition. In some sense, nowadays everything is automated with the help of a computer in the sense of CAD, computed analysis system. And the manufacturing is, if you order automotive right now, then you have a lot of options like the panoramic sunroof, the manual, or the automatic mission, or several options. It's all this kind of customization is available to the customers, right? And the management nowadays, they need real systematic engineering, systematic management. And the academics now is, they include electrical engineering and system engineering. Then what will be the expected viewpoint about the future derivative markets? Is some new concepts which we can wording about the possibility, but it's still possibility, but we can share the opinion that, future derivative market would be something different from now on. So this is a kind of preparation for this kind of changes. So basically there are many sectors, like non-financial sector, like multinational firm, globalized firms, or financial sector, personal wealth management, or power area, energy market, and some layers. That's not our main interest. For example, one stylized result is CAD for financial products, and we can visualize the financial product on the screen. And this is a timeline. This is some variation of the underlying prices. So you can design some derivatives on the screen and evaluate the performance on the screen. So what is the financial derivatives? actually I inserted some Chinese characters. So it's a financial derivatives that's basically derived products from the underlying variables, right? From underlying variable means, this, everybody can share the meaning. So this is individual stock price or stock indices or weather, it's like temperature, energy price, interest rate, or any other thing. So basically it's derived products. Okay? So this underlying variable itself, if you are interested in predicting the future of underlying variables, that's not the area of math. It's economics or finance, basically. Math, they handle the derivatives, which was derived from the underlying variables, and they assume that these underlying variables are given. So the pricing, derivative pricing means these underlying dynamics are given. Then using Monte Carlo, you generate a sample, and this the price of underlying, according to at the final time, what is the level of the price, you can evaluate whether it is zero or positive payoff, and then you generate millions of thousands or millions of sample paths and evaluate and average. That's the basic principle. Right, so it's basically random experiment. So the output would be this kind of point estimate with standard error, which is the starting point of constructing confidence interval. So this is basic mechanism. Of course, this kind of simple products, you can use some famous Black-Scholes formula or PDE to evaluate these products. However, it's a realistic products. So it's not total model, so basically you cannot apply directly the formula or PDE, cannot construct PDE easily. So with some principle, you have maturity, and within the maturity you have several the early redemption points, in this case 6 times, and it's a little quite complicated. So in this case, the Monte Carlo would be the only possible way. And specifically this product, the principle is not protected because the final line causes some loss of your principle. Okay? The securities companies issue this kind of products. The most important computation in such kind of business, that's the computation of these Greek values like first or second order derivatives. Why it is important? That's basically the result of Nobel Prize in economics. Black-Scholes formula, that's basically the basic background theory, suggests that based on this kind of value, you holding the shares, using these numbers, you keep the shares, then the business goes on. That's basically the conclusion of the Nobel Prize, the Nobel Prize winning theory. And this gamma, basically you are holding, or continuously in some sense, holding this amount of underlying asset means this gamma suggests that how much you sell or buy each time, because it's the change of delta. So gamma, that's basically how much buy or sell each day or each time instant. Okay? Here, so basically based on the Monte Carlo, we compute these amounts and we differentiate. The problem is here is the differentiation outside of the integral. So the question is whether we can exchange the order of operator, exchange basically the differentiation and integral. If it's possible, this kind of thing, if it is possible, then the Monte Carlo generates a very efficient estimator. However, if you cannot validate the exchange, then you have to sample these values, and then you use finite differencing scheme. And in general, that causes some instability of the Monte Carlo outputs compared to FDM method, the finite differencing method using PDE. However, nowadays, by the regulation authority to prevent some bad hedging operation of companies, they pose more and more restrictions or complications. So the PD approach is, as time goes on, very hard to apply in realistic situations. So Monte Carlo is the only way. So let's go on what the hedging is. Let's see. So the 12 is in some sense strike price, which is the underlying at time 1. If it goes beyond the 12, then the difference would be your payoff. In that case, there's a dynamic hedging, means you hold this dynamic number of shares as time goes on. So you always sell and buy some shares of stock, and automatically you need to borrow and repay from a bank account. So this is one way of seeing the dynamic hedging. So in realistic sense, it's I think it's more than 100 times. 100 times during the okay, 100 times. However, in actual financial company, do the rebalancing operation once or twice per day. So it's a little bit more discretized version of this graph. Yes, okay. So now the problem is how to compute the first and second order derivative from the value estimation. That's the big question in financial company, in the sense of financial computation. So yeah, this is some graphic result. So this is, this is some payoff, which is continuous. This one discontinuous. So this is the price. This is the first order derivative, second order derivative. And this one. You see some, if you see look in more detail, then there is some correspondence between these diagonal direction. Because if we differentiate this one, you get this one. Okay? So with this kind of discontinuous payoff, you have more difficult than that one. And the problem is, until delta, this seems in engineering sense, this might be usable in real world. However, with this value, this causes some problem in real implementation. So this is the more realistic products, which is called ELS, which is very popular in Korean market with the two underlyings. So this is typical grid values. And here the problem is this grid, this gamma means how much buy or sell each day. In this case, of course, this is a smooth surface. So there is some noisy, this is a noisy result. And you find that, sometime buy and sometime sell, that's very close, which means this is absolutely incorrect. So our approach is you have this kind of observation of noise output. Basically, this comes from Monte Carlo. That means it has its own confidence interval. Okay? Then, so basically up to now, what we did in finite difference, you just use these center points. That was what we did up to now. So the new way of doing this one is we take out the center point and we just remain the confidence interval and then build up some smooth curve within the intervals and use that points as the post-processed points of Monte Carlo. So use these points instead of this sequence of points. So using this approach, this is without such kind of post-processing with increased number of samplings. This one is the post-processed output. Okay?
We don't consider variation, change the variation.
Yeah.
As time goes on, the variation may change.
Actually, a little bit different because this one, every point is within the confidence interval. That's the basic limitation. So this one is, in that sense, is quite robust. So every improved points are within the interval, predetermined interval. So there is no such kind of trendy deviation. For example, this one is the, without post-processing, this is the output of the Monte Carlo gamma. It's after finite differencing, then you obtain, by post-processing, more smoother output. Now this one is for gamma. Yeah, so the basic mechanism of what we do is you have a price curve. This is gamma and delta, which is obtained by finite differencing. Then only considering the gamma curve, which is second finite difference of the original price surface, you get the feedback of improvement direction, and then modify the price itself within the predetermined interval, and then you iterate this scheme. And if the gamma shape is satisfactory, then you stop there.
You do it every day? Each day you update that?
Sure.
What is S1 and S2?
It's the underlying of two underlyings. This product is basically issued based on two different underlying. And then you get the first order difference, it's automatically smooth. So this is 400,000 samples without the fairing, post-processing. So in that case, you see that the gamma curve is from the 200 to minus 600. It's wide. Yeah. No, how can I say perturbed? Okay. Now, based on the post-processing, actually this one is the 400,000 times samples. This one is 100 million. And without any post-processing, it seems quite smooth. And yeah, it clearly shows you that, this gamma values are negative. Okay. However, in previous one is from 200 to minus 600. Now, this one is with 400,000 times with post-processing. Okay, this one is the previous 100 million, and this one is smaller samples with post-processing. And this one is post-processing with 100 million times.
This kind of scenario.
Yeah.
For each pair of S1, S2 values, you just estimate the values and
yes.
get
So basically, the Monte Carlo evaluates more than 1,000 points, the coordinate points. It's short. Anyway. So it's basically compared to previous. Of course, this improvement is not isolated points because we have a group of points, so it utilizes the information of neighborhoods. So basically, that's the basic idea of this new method. So it might be cons of this method. However, in real financial industry, they have a circuit breaking range of plus 50% or minus 50%. So in the view of today, the next day's price range is bounded domain. And actually the financial engineers in company, they did with increments of 1%, they evaluate all the possible values on day before. And then tomorrow they use that table for the actual trading. So this kind of group valuation and based on all the labeled information, such kind of improvement is very natural for current trading convention in financial company. So, okay, so this kind of things changes current financial companies, not a few times, basically from impossibility to possibility. It's a huge improvement in such sense. This is some computational results, and basically the simple options is robust, but sometimes it gets worse in the minor case. However, with the complicated one, it reduces a lot. So finally, nowadays, I believe that the current many sectors or many industrial areas, they need mathematician. However, not pure mathematician in some sense. They want some person with being smart in mathematics, and at the same time, they want someone who can implement what they are talking. Basically, some coding ability. So if combination of math and IT, that would change a lot of nowadays industry. Not only finance, but some other areas, I think the same thing happens. Yeah. Basically, the fairing for Greeks, I'd like to add the last few words. The fairing, the words comes from automotive industry. Basically, the original styling in automotive industry, they shape the clay, which is it's clays, kinds of soft material. So they make a shape and make it seems like looks like automotive, and then paint and do everything. And then all the CEO of the automotive company approve the model. Then with the three-dimensional digitizer measurement machine, they digitize hundreds of thousands points of the whole shape. And from the shape, they reconstruct the differential surfaces. Now, the digitizer, the most famous company is Carlo, which is famous for optical things in Germany. Basically, all the measurements involve measurement error. So it's noisy, and from the noisy inputs, they need denoising. And what we adopted here, that's basically the same idea, which is denoising automotive company in this case. So it's a kind of fusion ideas from the Monte Carlo or the risk control evaluation framework, which is very fundamental in financial mathematics, and which is very popular techniques in automotive engineering in some sense. So we combined them, and currently, at least Korean companies are very happy with that result. Okay, that's